This video, we're going to be looking at enthalpy change and heat of reaction. They are actually basically the same thing. But before we continue, please do well to click on the subscribe button below there so that you can get notification of our classes. Now, we start with definition of terms, so that you can get an understanding of the whole concept. Now, heat. Heat is a form of energy that is transferred from one body to another due to temperature difference between them. Okay, so that is what heat is. It's a form of energy that is transferred from one body to another as a result of a temperature gradient or difference between them. Now, the next is enthalpy. Okay, now enthalpy is the total quantity of heat absorbed or released between the start and the end of a chemical reaction. Okay, so you can see there that the enthalpy of a system at constant pressure is given by delta H equal to the final enthalpy minus initial enthalpy, which you can also see as delta H equal to the enthalpy of product minus enthalpy of reactant. Now you should note this, that when heat is absorbed, that is delta H is positive, so that's heat added to the system, the reaction is endothermic. Now, but when heat is released, the reaction is exothermic. When heat is released, it means that the enthalpy change is negative, the reaction is endothermic. So in this case, we have a reaction can either be endothermic or exothermic. Endothermic when heat is added to the system or when the system gains heat. Exothermic is when heat is released from the system or when the system loses heat. Now the next is heat of reaction. Heat of reaction is the enthalpy change at constant pressure. You can see, so they are interchangeably. You can interchange them. They can actually be used interchangeably. You can see that. Now we see the systems. What are systems? A system is the vessel where the reaction of interest is taking place. Okay, it is the part of the universe that the scientist is interested in, and the system can be open, closed, or isolated. Okay, so and when you talk about a system, it means that part of the universe that the scientist is interested in, that you're interested in. If you are cooking, let's say you're cooking in a pot, you're interested in the food inside. Okay, so that is the system. Now we have three types of system. We have the open system. In this system, there is a loss in both matter, that's mass, and energy. So matter can be lost and energy can be lost. A good example of an open system is where you have, let's say you're cooking with a pot open, or let's say you have a reaction taking place in a conical flask or in a beaker and it is open. So energy can be lost, matter can also be lost. Now, the next is a closed system. In this system, there is loss in energy, but there is no loss in matter. Now, a good example of a closed system is where you have, let's say, a beaker now that has a stopper. A stopper, that means something to close the mouth of the beaker while the reaction is going on inside. So matter cannot be lost, but energy can actually be lost because when you, in some reactions, when you touch the beaker, you see that it's hot. Being hot there means it is losing energy in form of heat. So energy can be lost, but matter is not lost. Another good example is when you're cooking, the food inside is the system. Now, when you open the pot, it is an open system, but when the pot is closed, you can see that as a closed system. Now, we have an isolated system. In this case, there is no loss in energy, there is no loss in matter. In this very case, the system is completely sealed such that energy is not lost and matter is not lost. A good example is your lagged calorimeter, when it is lagged, fully lagged, or when you say a vacuum, like a vacuum flask where matter is not allowed to escape, energy is also not allowed to escape. Okay, so that leads us to surrounding. What is surrounding? This is everywhere outside the system. Okay, it is the part of the universe which encloses a system, and it is directly or indirectly in contact with the system. Okay, so you have your system. Any other surrounding, any other thing outside is the surrounding. The factors, is the surrounding. The temperature, the pressure, whatever it is, anything outside it is the surrounding. Now, but there's something that separates the system from the surrounding. That's called a boundary. Boundary is the interface between the system and the surrounding. Okay, that separate the system and the surrounding. So that means in this case, or in this term, we can divide the universe into three aspects. Part of the universe is the system, which is what we are interested in. Then we have the surrounding, which is what is around the system. Then we have the interface, which is the boundary, which separates the system from the surrounding. Okay. Now we see the next, which is heat capacity. Actually, heat capacity is the energy required to increase the temperature of a sample by 1 degree. Is either you increase it by 1 degree or increase by 1 Kelvin. Okay, and heat capacity, that's the formula for heat capacity. Let's see that again. That's the formula for heat capacity. C equal to H all over mass times change in temperature. Okay, so that now leads us to some questions here. Now here we are told that the enthalpy change for the combustion of acetylene. We are asked to calculate the enthalpy change for the combustion of acetylene. Now we can't do this unless we write the balanced reaction for the combustion of acetylene. The balanced reaction here is C2H2 plus oxygen. Now whenever a hydrocarbon reacts with oxygen, you are going to get carbon dioxide plus water, CO2 plus H2O. The equation is not balanced, so we can do well to balance it here. To balance the carbon, we have 2 here. Hydrogen is already balanced, but the oxygen, on the right hand side, we have 5 oxygen, so we can come here and make here 5 over 2. Now, since we don't want to leave our answer in fraction, we can multiply through by 2, so we are going to get 2C2H2, okay, plus 5O2, giving us 4CO2 plus 2H2O, okay, multiplying through by 2. Now, we want to calculate the enthalpy. Remember, we say that the enthalpy of reaction, the enthalpy change or the heat of reaction is the total heat of the product times the total heat of the reactant. And you should also know that the heat is affected by the number of moles. Okay, so if you look at here, the enthalpy for CO2 is minus 393.5. So I can come here and write 4 times minus 393.5. Okay, that is what we have for CO2. Now for water here, we have 2 times, because we have 2 moles of water. So 2 times minus 241.8. Okay, 0.8. Then now the enthalpy of a pure element, oxygen here is 0. Any pure element, the enthalpy is 0. Okay, then while for C2H2, which is the acetylene, we are going to get 2 times 227. Okay, so with this now we can see that the total energy of the reactant is 454. That's what we have here. Then the total energy for the product, if we calculate that, we are going to get, let's do that quickly. We are going to get 4 times 393.5. Okay, then plus 2 times 341. 2 times 241.8. Okay, that is 483.6483.6. Okay, that gives us 2057.6. So this is minus 2057.6. So according to the question, enthalpy of product, according to the formula, enthalpy of product minus enthalpy of reactant. So that is going to give us minus 2057.6. Then minus, that's the product, minus the reactant is 454. And we are going to get 454 minus 2511.6, minus 2511.6 joules. Okay, now we see that. So that leads us to another question. We asked to calculate the enthalpy change for the reaction CO2 plus water, giving us H2CO3, and we are given the standard value for the enthalpy of formation as follows. Okay, the CO2 is 393.509, water is minus 241.83, and H2CO3 is minus 275.2. We can do that quickly. Here we have CO2 plus H2O giving us H2 CO3. Okay, each of the species here has 1 mole, so we can just quickly write. For here we have minus 393.509. For water here is minus 241.83, and for H2CO3 is minus 275.2. So let's add together that of the reactants. So we have 393.509 now plus 241.83. Okay, now we get 6 minus 635.339. Okay, so this is 635.339. That's for the reactant side. And for the product side, we still maintain minus 27275.2. Okay, so if we follow the definition, enthalpy of product minus enthalpy of reactant, we are going to get minus 275.2, which is the product, then minus the enthalpy of reactant is minus 635.339. Now don't forget that minus minus there gives us plus. So when we do that, we are going to get, we have 275.2. Now we are going to get 360.139. So that is equal to 360.139 joules. Okay, that's a good one there. Now we see a question here. It says that they calculate delta H of a piece of metal with specific heat of 0.98 kilojoules per kilogram per Kelvin, and a mass of 2 kilogram is heated from 22 degrees Celsius to 28 degrees Celsius. Remember we said something about heat capacity, which when we can see that delta H here is equal to mc theta, when we make heat subject of formula. So our heat here is mass times specific capacity times temperature rise. Our mass here from what we have is 2. Now our specific heat capacity from what we have here is 0.98. Okay, now multiplied by the temperature change is from 22 to 28, so temperature change will be 28 minus 22, and that is giving us 6, so times 6. So if we calculate that quickly, we are going to get 2 times 0.98 times 6, and that is giving us 11.76. So this is 11.76 joules. Okay, so that is the answer for that. That's the value for the enthalpy. Now it leads us to another question here. We are given that when a 6.5 gram sample of solid sodium hydroxide dissolves in 100 grams of water in a coffee cup calorimeter, the temperature rises from 21.6 degrees Celsius to 37.8 degrees Celsius. Okay, calculate delta H in kilojoules per mole of sodium hydroxide for the solution process. And we are to assume that the heat of solution, specific heat of solution, or specific heat, capacity formed is 4.18 joules per gram Kelvin. Now at this point here, our mass, we still use our formula delta H is equal to mc theta. But now our mass is a combination 6.50 grams of sodium hydroxide and that of water 100 grams, because the temperature rose when this was added. So we are going to get the 106.5 grams. Okay, so you can write that there, that the mass is 106.5 grams. Then we are given the temperature rise. The temperature rise here is from 21.6 to 37.8. So that means the difference in temperature will be 37.8 minus 21.6. Okay, and that is going to give us 16.2. So my theta here is 16.2 Kelvin, or degrees Celsius, sorry. You can write that down. But also note that the change in temperature in Kelvin is the same thing as the change in temperature in degrees Celsius. So I can say 16.2 Kelvin. I can also say 16.2 degrees Celsius. They are the same. Don't forget that. Now we are also given the specific capacity. So if we are to substitute values now, it means that my heat delta H now is equal to the mass. The total mass we saw there is 106.5. Now multiply by the specific heat capacity of the solution is 4.18. Okay, now multiplied by the temperature change is 16.2. Okay, so if we do that now, we are going to get, let's calculate that quickly. We have 106.5 now multiplied by 4.18, now multiplied again by 16.2. Okay, 0.2. So we get 7,211. So we are going to get 7,211. That means 211.754 joules, which if I want to convert to kilojoules is going to be approximately 7.2 kilojoules. Now, but if you notice here, we are asked to, this is in kilojoules, but we are asked to leave our unit in kilojoules per mole. Per mole there means in 1 mole. So you can write that somewhere that delta H is 7.2 kilojoules. But if we are to go further there, we'll see that the molar mass of sodium hydroxide is equal to 40. Okay, sodium is 23, oxygen is 16, hydrogen 1, so that gives us 40. That's the molar mass. So we can say that 6.5 grams, of sodium hydroxide is releasing 7.2 kilojoules of heat. So now we have 40 grams, which is per mole. We want to see the amount of heat for 1 mole. We can call that X. So we now see that X is equal to 40 times 7.2 divided by 6.5. So we see that quickly. So we have 40 times 7.2 divided by 6.5. So you see that we get 44.3. So the answer is 44.3 kilojoules per mole. Okay, for 1 mole. Now we are going to see another question like this. It says calculate the heat of reaction delta H for calcium chloride dissolved in 50 cm cube of water caused a rise in temperature of 3.4 degrees Celsius. So here the same thing. We are asked to find the heat of reaction actually in kilojoules per mole. Now, but if we are to continue with that, first of all, we can see